Where is the microphone? Huh? Which one? This one?
Yeah.
Yeah, and it's a wide microphone.
It's a wide
Just
one.
speaking to
Okay. Well, good afternoon, everyone. I would like to thank, first of all, Mr. Benicio Golart, who was able to organize with Unicamp this type of lecture. I would like to welcome people from El Dorado Institute and Motorola, as well as from UFAM in Amazonas and other entities that will be interested in the subjects that we will discuss today. I have the pleasure of introducing Professor Alexander Dimitrov, who is a professor in the Department of Mathematics and Statistics at the Washington State University in Vancouver, Washington. Professor Dimitrov is a very old acquaintance and friend of mine, alumni from high school, and one of the smartest people that I know from high school. He managed to graduate with flying colors the Sofia University of Technology in Bulgaria. I'm sorry, the Sofia University, not Institute of Technology, the University of Sofia. And after that, he was admitted in the University of Chicago, where he holds a master's degree in physics and a PhD in applied mathematics. As such, I would like to welcome him here, and basically I'm very much interested in the neuromorphic computing as well as the new concepts of which Professor Dimitrov has a lot to tell us. Thank you very much.
Thank you very much.
Please have the floor.
Thank you for having me, and for thank you to all the online audience. So this talk is about our research in neuromorphic computing. It's a continuation of my previous research in mathematical neuroscience. There are many connections between the two, but also the slant of the research is in that direction. To introduce first neuromorphic computing. Okay, something disappeared there. Is that me? Okay, I can do that as well. But neuromorphic computing is a novel strand of computing which is getting inspiration from how the brain works, and it's modeled. The new thing here is that it's modeled after brain dynamics. It's working with stateful neurons. I'll contrast that with standard neural networks and deep neural networks. So that's part of the new developments here. We started from interest from our previous research on modeling actual neural tissue based on data. So in neuromorphic computing, we saw a new way of looking at the same problems, simulating and predicting neural activity, and on biomedical side, simulating and predicting biomedically relevant signals. So one of the topics we had there is that possible to do with neuromorphic hardware, and how well can we do it? Especially for biomedical signals, it's very important to the simulations to be precise because people's lives depend on them. On the other hand, a lot of that is large-scale signal processing of various signals, and that brought to the joint interest with Mr. Ivanov there and Motorola, which is how well can we do signal processing as well on various different levels. Another reason for our interest and motivation in case was some, so I'm putting that here to highlight this interest, some initial simulations that highlighted the benefits, major benefits of neuromorphic computing. So in this case, I work with Intel's Luigi processor. In Luigi 1, we run, so when starting to work with Luigi 1, we run what is essentially identical computations on a HPC, server class CPUs, and on the Luigi CPU of simulated spiking neural networks. And here are the results there. First, we start with 1.5 orders of magnitude benefit. This is the standard simulation, and this is the Luigi simulation. And then the standard simulation increases in complexity. This is a log-log scale, so it is super power law. On the other hand, we're very excited to see that, yes, there increase in computational time of Luigi, but with much better scaling because of the design of the chip, because of the specialized electronics of the chip. At the end, leading to a discrepancy of 3 to 4 orders of magnitude in performance. So that was very interesting. In Luigi 2, that's the date below, unfortunately, things got a little bit worse, in part because the standard simulations improved a lot. So standard computing architectures don't stay at a fixed level either, and in part because Intel changed a lot of the software stack, and they're still having problems with some of the compilers, so that led to a not improvement. But anyway, those are all things that are fixable, and the architecture is still very much comparable or superior to standard computer architectures. Intel also did a lot of research with other groups and their in-house groups to try to identify problems for which the novel architecture is competitive or outperforms standard architectures. Mostly what they found out is standard problems from machine learning with deep nets. They don't do that well on Luigi. It's different architecture. The problems that where Luigi shines and where it outperforms pretty much anything known are problems that can be formulated as recurrent neural networks. Again, that's the structure of the electronics in Luigi. It has the neurons there, the individual units, have internal dynamics, which maps well on recurrent neural networks. And those are the things that don't work that well, but other does. This is an important, we need to take into account not just speed, but the power requirements of that. So the improvements here in terms of delay power products. Again, because of the specialized electronics, it provides very good results when the problems that are computed are a good match to the architecture. Otherwise, things have to be done more carefully. Okay, so why now? There's been tremendous progress in both neuroscience, the basic neurobiological work, and in neuromorphics. In neuroscience, over the last 20 years or so, when I was active, things changed a lot. There are now massive neural data sets. So there's the era of large data in neuroscience. When I started, that was the era of many theories, but little data. So now there are fewer theories because all the rest went away when the data came. What are coming are massive neurostructural data sets. So we know better and better how the brain actually is connected and the structures in the brain that perform different function, and improved understanding of single neurons and single synapse, single connection structure. Parallel with that is the progress in neuromorphic computing. So now there are several analog and digital chips with good user support. There is research hardware like Spinnaker and brain scales, but there's also emerging commercial hardware, of which Luigi is one example. IBM before that came with True North, and now there is a different architecture, North Pole. There are analog chips that are emerging, like Dynaps. All of them coming from the commercial side, usually, but also from the research hardware, good user support, and increasing libraries with which things can be done. So the neuromorphic technology is presenting a new model of computing. To me, that's the novelty, the several novelties. The main novelty for me is the computing with dynamics, that individual units there have their own intrinsic dynamics. It is controllable to some degree, but it does whatever it does. And less so in Luigi because that's still a digital architecture, but in the analog ones, there are electronic elements, current flows, they're usually subthreshold. So the current flows as the physics tells it to flow. One of the interesting questions when you have computing with such elements, so that's going to be each individual unit, but they're connected in some form of computational graph, usually directed connectivity graphs. The network that emerges from there has its own dynamics that's to some partially driven by the unit dynamics and partially driven by the connectivity of the network. What can be computed with things like that, and how do we compute it most efficiently? Eventually, we also have this graph evolving. That's usually called learning, but it's yet another dynamical system that's evolving on a typically slower time scale. On the other hand, this is not absolutely new architecture. They're old models. Analog computers of the past were trying to do that. Engineers there encountered great difficulties parsing the programming. I was in the museum in Palo Alto, computing museum in Palo Alto, where I saw analog computers. So the programming was you take wires and you plug them in different places. It wasn't easy. On the other hand, digital computers at that time were programmed in a similar way, where people went and flipped switches up and down. So they started from about the same level, but this architecture had more issues, more difficult to configure, prone to noise. The novelty here in the neuromorphic structure is at least it's using structures and primitives for which we have some guarantee that it's working, because it's brain-like, and we tend to believe that our brains work. So this has some chance of working. The main the main structure there, which is helping specifically to control noise, is this event-based computing, where each unit emits a spike and then resets to a known stage, so that the noise that normally analog computers accumulate is controlled here. So the current neuromorphic systems that are ready to use, there are a couple of analog ones, Brain Scales 2, that's in Heidelberg. It's a research system. Dynaps is a commercial analog system from Synsense. And on the digital side, we have Luigi and we have Spinnaker 2. Both of those are, Luigi is from Intel, Spinnaker 2 started as a academic research enterprise, and then a company was spun off, SpinCloud, that is planning to use it and already has some use cases as a commercial enterprise. There are several other ones. I'm not going to talk about them. Things like T1, Akida, Recon, mainly research support chips with less of a software and user base. Other things that were very exciting technologies, Neurogrid, Rollsin, Tianjig, are mostly defunct these days. And in many cases, only the developer could program those because programming involved oscilloscopes again, less of a software support. The main these days labeled with AI accelerators, NVIDIA, Google's TPU, GraphCore, Intel also has intelligent processing units. This is the name these days, or neural processing units. They're mostly for deep neural networks and are optimized multiply, accumulate, and nonlinear functions that are typically used for deep neural networks. And North Pole is somewhere in between. True North was a spiking chip with dynamics. North Pole maintains some of the neuromorphic part and some of the feature of, I'll switch to here, the common ones. Some of the feature of neuromorphic systems, which is neuron models are stateful. In North Pole, they don't have internal dynamics. It's like standard numeric simulations. The neuromorphic chips that we're interested in have on-chip learning support, so this weight dynamics is supported by electronics on the chip. Again, North Pole doesn't have that. It's a pure inference engine. And neurons of the devices that we're interested in communicate with events, and typically sparsely in time. And finally, the main feature of most of those architectures, they have many cores. Usually there are thousands to millions of those units on chip, in a single chip. Computing memory, so everything is local memory. You can think of it as one big cache for those things. And network on chip that is designed to scale so those chips can be tiled. And the overhead for communication to other parts of this system is, the network is designed with intentful overhead. So, relatively quickly about analog neuromorphics. I mentioned briefly, but they use subthreshold dynamics in either classical electronic elements like diodes and transistors, or some are trying novel electronics elements like memristors, spintronics. But all that away from the CMOS idea of just having switching elements and only ones and zeros are there. Typically, here's an example of the BrainScales chip. Typically, they are hybrid systems where the computation is handled in analog manner, but the interaction on the computational graph, this communication with events, is done with a digital network. Again, typically that will be an asynchronous network. This was the engineering abstraction of the brain structure, where that connectivity is done by just growing wires from here to wherever you need them. That turned out to be very, very difficult with electronics. But the network is providing a very nice substitute for that, that allows us to continue thinking in that level of comparison, neuromorphic to neural. Just an example of what elements are in the BrainScales chips. You can see variable resistors, you can see capacitors, op-amps are all there, and so currents just flow the way they would flow through those elements. I focus more on digital neuromorphic, but I also consider them transition technology because the analog ones, they're more difficult to tackle, but they have even better specs once we know how they work. The scary part there is noise and lack of persistent state. Part of the instructions on how to program BrainScales is, let's do calibration today to see what the elements are actually doing. So, did that. So we started with Lihi 1. some number of cores, some number of neural units per core. What was very interesting for us at that time is this boundary, more than 2,000 connections going out of a single neuron or coming into a single neuron. On the biological side, that was exciting because that was already in electronics implementing graph complexity that we saw in mouse brains, and it's approaching the graph complexity of humans, where humans usually have of the order of 6,000 to 8,000 outgoing or incoming connections. So we could see how we could easily get to, say, modeling human brains with that, as compared to, say, TrueNord, IBM's chip, that only had 128 connections. Luigi 2 improved on that, so about the same number of cores, but 8,000 neurons per core. That's on Intel 4 nanometers, I think. So just scaling down the electronics sped up the things a lot. It added programmable neurons where previously the dynamics was configurable but relatively fixed. Enhanced learning. So all in all, electronics was better. Why do we think of it as transition technologies? They are very capable, very fast simulators. They do have many features, many hardware features that we find desirable from the modeling perspective. So like neural simulations, synaptic dynamics, synaptic simulations, configurable neurons that are more or less naturally match models that we've been, we, in the sense of the community, has been running for the last 20 years at least, maybe 30. This on-chip learning was very exciting, with many of us still not using it, but the fact that it's there and allows for the learning mechanisms that are built into the electronics is very desirable. It has simulated noise sources. Essentially, every neuron has its own random number generator if it's needed. In some cases, it's needed, I'll highlight. And relatively stable API. It's still digital, but tools developed here with this persistent technology and persistent state can be used to experiment in the analog situation before we actually port it to analog, where there are additional challenges with non-persistent state, with effects of temperature, etc. So I have a few slides here from Intel stacks, just to highlight to everybody where Intel wanted to go with those chips. So as you can see, they do have a desire to go from edge to cloud compute. On the other hand, this is still an accelerator, so it will be in hybrid systems along with the standard CPUs. Probably not a good idea to try to do web page rendering with neuromorphic computers. But that's what we're seeing now. NVIDIA and the other neural processing and tensor processing units are doing exactly that. They're accelerating certain part of the computation and leave the CPU to do something else. Goal again being achieve brain-like efficiency. Part of the goal always revolves around energy usage, and Intel's desire is to achieve competitive computations with order of magnitude lower energy budgets. Then part of their trajectory, those are the features: compute and memory integrated, stateful neurons with built-in dynamics. That was a big revelation on the engineering side. Event-based communication improves a lot the network and simplifies a lot the requirements for the network. compare that to either recurrent neural networks or deep neural networks where the communication is dense. The whole layer needs to be transmitted to the next stage for processing. Here, communication happens from time to time, and a lot of the computation is local. Those features, sparse connectivity is one of the features that allows for such sparse temporal communication as well. Ability to do on-chip learning, and all of that being asynchronous, including the computation. Some of the highlights, difficulties with Luigi. They stuck to do that energy budget, they stuck with fixed point arithmetic rather than floating point, which for us is no big deal. Floating point is necessary if your models need to do something from subatomic particles to galaxies, but in neural computation we know we're from the reset to the threshold, so that's not a big deal. But still, it requires a little bit of flexibility. They don't have multiply accumulate, that's the big accelerator for deep neural network accelerators. Here, what replaces that is the intrinsic dynamics of the neurons. That is enhanced. And for now, at least, that there is no off-chip RAM. The on-chip RAM is SRAM, so it tends to be expensive. So those things tend to be, the chips tend to be more expensive than equivalent Intel CPUs, for example. But from what I hear, these days systems on chip start having RAM on the chip as well. So everything is moving in similar directions. And other commercial chips like Spinnaker, they've taken slightly different made slightly different design choices. So they have onboard fast RAM, but they also provide for common DRAM that with which the chips can communicate and have larger scale, solve larger scale problems. Again, for our friends in Motorola, several of the tasks that Intel engineers and other colleagues found suitable for Luigi involve programming, so they have now binary unconstrained and quadratic programming solvers, and here are some of the specs. So one particular problem doesn't matter what it is, it's some little robot here, but in one particular problem they achieved about 80% faster compared to current level server CPUs, and much lower energy, about 300 times lower energy. So a little bit about the structure of Luigi. What do we have? We have neurons in electronics. Those do the computation part. Intel introduced microcode as way to configure more complicated dynamics, and that's slowly filling up. So my impression is, of the computational electronics, about half of it is the synapse with built-in learning mechanisms. That for now is one of the less utilized portion of Luigi, but it showcased capabilities of that group and is driving research in that area. So we have LF neuron. What the LF neuron does is does some dynamics, reaches a threshold, generates an event, and then that event is passed on the communication substack. That event then arrives at the synapse and triggers some synaptic response, and if learning is turned on, can trigger synaptic dynamics as well, and the synaptic response comes back to the neuron. That's usually input from other neurons and modifies the neuronal dynamics. Luigi 2 also introduced a new API, which is very interesting as an API. It's a hybrid computing system, allows for declaring computations on CPU, on GPU, and on neuromorphic processors. They promised multi-time domains. I don't think anybody has used that yet. So we can, meaning some way to coordinate those different architectures for time-sensitive applications, where things that happen here actually, if they happen at the same time as things with the neuromorphic, those two systems can coordinate that information. Again, a little specifications. I'll leave the presentation at some point so you can look at them if you're interested. I'll highlight a few of them. So that's one of the increase from 128,000 neurons for Luigi 1 at about 1 million now. About the same number, of course. That was a little bit underwhelming for us. The local memory that is usually used for configuration and for storing synapses, storing the connectivity of the graph, they've kept relatively small. On the other hand, they increased the ways that this network can be connected, including random connectivity generation on chip, so that speeds up a lot the creation of the network. We're still not using it because we're doing some research work. However, I'm experiencing delays if I compile on a standard computer. Even relatively small graphs take a long time to compile, so it'd really be nicer if all that creation can happen on chip. And no, there was another one that I wanted. Oh yes, they introduced convolutional mechanisms to allow for limited resources to be used to create larger computational graphs. That's repeating to some degree, but it's useful to repeat. Common threads there. There is intrinsic dynamics, stateful neurons, versus the deep neural networks where input comes, there is a big matrix vector multiply, nonlinearity, and it continues. A particular layer does not remember anything else. It does not use its previous state. And the event-based coupling, where what's communicated to other neurons are those spikes, those events that are generated from time to time, versus deep neural networks where at every computation the whole state of the network has to be communicated, so that's a heavy-duty communication to other parts of the network, or needs a big chunk of shared memory so that all parts of the network can have access to that state. I already motivated a little bit why to work with SNS, but it's a good question. So those are not necessarily the easiest thing to do. Even recurrent neural networks are less familiar. And now we're saying, okay, recurrent, but now you're only going to work with spikes. And so it's good to know what artificial neural networks and deep neural networks can and cannot do. So they can do some very good things. Those are old work, disstatement, multi-layer feed-forward networks. They were called perceptrons at that time, but this is good. Are universal approximators. That means any function of an input that produces desired output, they can approximate. And that was known in '89 already. On the other hand, this is relatively new work, which again highlights, yes, they can compute anything, but do we have an algorithm with which to reach that desirable high quality state? And that group claims that generically no. Again, that's work from about 2 years ago. The summary of that, we can prove the existence of neural networks with desirable properties. Can we find a training algorithm to reach that state of the network? The answer is generically no. And I'll highlight. But the take out from that is they exist, but there is no algorithm that can reach that state, including probabilistic algorithms. So it's a relatively strong statement. Let me try to parse it a little bit finer. Those guys, not our work, but I'm very impressed by them. Those guys provide additional classification on the space of all possible neural networks, and found that there are subsets that are trainable, and they can be trainable with very little data, including one datum. You give one example, and the network is done, trained. But that continues with, some are trainable with 2, some are trainable with 3, and some are only trainable with arbitrary large data sets. And there is a large class of networks that are not trainable at all. Even finer, trainable with what precision of your cost function. And here, some of those start overlapping there. Again, some are trainable with very little data and can achieve very high accuracy, but the generic result was that none of those are trainable with any precision that you pick. But with infinite amount of data, you can train them with 1 digit lower precision, and with some fixed amount of data, you can train them with 2 digits lower precision. So again, it's not a super clear-cut statement, but mainly it's a statement that people have to be careful when training deep neural networks, because usually the interesting ones are of the class that are not trainable, in which case many of the issues plaguing deep neural networks, that's a theorem stating you cannot resolve them. So you're always going to be open to adversarial attacks, you're always going to be open to hallucinations, and various other things that I'm not following very closely. But whatever problem emerges, this is suggesting that it will probably be, it's not a bug that can be called it out. It's a feature of the architecture. To continue, on the other hand, recurrent neural networks, and as part of them, spiking neural networks don't seem to have that problem. So that's, again, from about the same time, early 90s, the computational paradigm of reservoir computing came out with statements that you have a recurrent neural network, very mild constraints on it, so that it does something interesting. Then a linear readout can produce a universal approximation state. And we know how to train linear systems. That's essentially trivial. Without modifying any of the architecture, just the dynamics is so rich that you can pull out solutions of problems from within the dynamics of the system. So that the first was about recurrent neural networks, then Maas and Markram came up with equivalent result for spiking neural networks, and later on a colleague, Catherine Schumann, and her collaborators came out with statement that's near and dear to all computer scientists. Recurrent neural networks are, in this case, they call the neuromorphic computing is Turing complete. So we actually can render pages with neuromorphic computers. It's just probably not a good idea. Versus deep neural networks that they don't have loops, they have something like decisions. They're not Turing complete. If you include learning, maybe you have to think, but that's a constraint. So I'll continue with the specifics of one class of spiking neural networks and mapping those onto Luigi. So this is an example where we started with, on the biological side, typical neurons are pretty complicated objects. Here's an example of dynamics of those objects. How does it look like? There is internal subthreshold dynamics and the events that the object generates. Typically at this level, we simplify that a lot by having a point neuron with some dynamics, although a different balance between resources and constraints, we can have more complicated neurons. And at least in Luigi 1, this point neuron had relatively simple dynamics. We have to speak differential equations. Voltage dynamics, rate of change depends on the current, and some of those are. This is linear, so yes, that's all there is. There are several enhancements that make for more interesting dynamics. Even that was sufficient for some of the work that we're doing. I'll summarize some of our published work. That's from these days Doctors Regionidae. Part of it was mapping and validating the individual neurons on the hardware, and part of it was looking at the sensitivity of those maps, how sensitive is the neuromorphic simulated dynamics to changes in parameters as compared to the standard simulations. We're in good state because we have the ground truth. And for us, the ground truth is simulations that happen on classical computing architectures. Those have been done a lot. There are many examples, many known results. And whenever we need something, we run the simulation, we get it. So we can generate a lot of data. We have a lot of options for validations and comparison. The main tool that we used at that time, we're collaborating more closely with the Allen Institute for Brain Science in Seattle, so they had the BMTK. Later on, turned out the backend for their computational system is another software package called Nest, one of the backends, and so we started comparing directly to Nest. I mentioned that as well. This is the scale of networks that we're interested in. That's about the size of like maybe 20% of mouse visual cortex. So they're interested in the basic science. We're thinking, well, if we can copy the mouse visual cortex and have it run on Luigi, then you have a ready-made visual system you can put on a robot, and it knows how to run away from cats. That must be good. So, and the comparisons, classical LF models, anything we write with differential equations, we can put on numerical computation in a computer. This is the standard formulation. Luigi conceptual LF model turned out to be slightly different. They don't use capacitance resistance, they use a time constant. Okay, that's trivial. There is the current state here. Well, the current state here is scaled by some capacitance number, so we have to think about that. Otherwise, the rest is the same. Reset in Luigi in this stage happened only to 0. Here the reset happens to some reset voltage, so how do we deal with that? that there is always comparison to threshold, but the other minor changes change the meaning of that threshold. So what we ended up doing, that's probably not that interesting. What we ended up doing is, on top of that, that's the conceptual model, but when you look closely in what Luigi is doing, it's a form of finite state machine with specific parameters. So this is the Luigi LAF finite state machine. Next time we look at the state, it's the previous time. There is some decay function with a decay constant. There's no time constant anymore. They were just pretending there is one. There is a bias current, and the bias current is in here. It's not in the current. And then there is a current state that's added to that. Looking at that, we started seeing, well, that looks a lot like a classical numeric integration scheme from differential equations. So I can write one here, and then it starts, we can start matching parameters. Here we have tau, here we have delta v, so 1 over tau, here we have delta v over 2 to the 12, y2 to the 12, go ask the Intel engineers, with details. Here I have the current state multiplied by dt, so that must be matched by the by the current state for the Intel for the Luigi. Ultimately, we came up with affine map, so it's a shift and scale. This voltage state for Luigi is the LF voltage, however shifted by R, by the reset voltage, so that we have a reset to 0 in Luigi. And we have an arbitrary scale because we don't have floating point, so we need to control the precision with which the representation go into the integers states that the processor provides. That gives us that. The membrane current, it's a scaled version of the model, and the bias should be put all in here and some voltage values, and multiplied by dt because Intel doesn't talk about that is step 1, but we may want to have finite control over the representation of time. Equivalently, decay constant is connected to both the time step and the time constant, and you see how now we have a non-dimensional unit, time over time, that already matches well the non-dimensional units in Luigi. And the threshold is again shifted threshold, scaled by the same amount, so the comparison can be made in the same way. Given that, I'll talk about the forward and backward mapping. So that provides us mapping from standard parameters to Luigi parameters. That's invertible, at least in terms of continuous variables, it's invertible. We know that the mapping is not fully invertible because all the states and all the variables in Luigi are some fixed integer precisions, and so there will be holes in the number system. As they are in floating point, they tend to be smaller, and usually practitioners ignore them as much as possible. We can't here. Some results. This is what the classical simulation does when we do the when we run it. This is what the Luigi simulation does when we do the translation and then map back the result to compare directly. So they're pretty good. That's one way of stimulating the system. Here is stimulating the system with impulses, pretending they come from other parts of the system. So you can see here it's a good example to see what happens when those spikes that are generated by the neuron arrive at another neuron. There is change in the state that's described by some function, but it's simulated in the system. And you can see the events. There's an event here, another event here, 1, 2, 3, 4, 5 events coming, etc. Of course, good to look at things, but also good to compare with numbers. All those are pretty close. Correlation coefficient is almost 1. Find a measure, root mean square. It's about 10 to the minus 4 millivolts per millisecond for the whole trajectory. Looks good. On the other hand, like standard computational errors tend to be of the order of -8, -10. So this already shows some discrepancies and leads us to do other research as well. Can be lower than that. There's some ideas along that well. Basically, we give that. If it's sufficient for your work, great. If it's not sufficient for your work, don't use Louis. Or wait a little bit, we'll have better approximations. The next part that we did was sensitivity analysis of those models. Again, the idea there comes is we have some result. Now we want to see how stable is this result under perturbations of parameters. Mostly we use computational versions of that, so there is Morris's 1 at a time, 2 at a time method. They're descriptive, so basically we change one parameter at a time and compare it to the known system, or change 2 parameters at a time and compare it to the known system. 1 parameter, 2 parameters, both of those 1 parameter results are very encouraging, showing that yes, at the parameters where we expect, the error is minimal, and this has a quadratic response curve, so in the neighborhood it produces about the same dynamics as well, which is beneficial. This one of the parameters, this is the threshold parameter, turns out to be important. You see that the response curve is sharper, so that means this has to be dealt with more carefully and better find the minimum more precisely, because then it more rapidly changes. That's reflected in the quantitative measures as well. In both of those, the RMSE at the bottom was about 10 to the minus 5. Sorry, the RMSE at the top, the maximum changes that we investigated was about 10 to the minus 5. In this one, it was 0.2, so 10 to the minus 2. So for that parameter EL, the sensitivity was much higher, which again directs you to a place where it's worthwhile devoting resources of finding a good representation, compared to those 2 parameters that, if you're about right, it's probably okay. They are related, so the 2 at a time is essentially giving you that curve, but in a different 2-dimensional direction, and there is a little bit. This is even less sensitive than the other side, in the other direction. Those 2 again tell you roughly the same story, that there is a very high sensitivity, meaning system is sensitive in that direction, but not in the other direction. We did that on both cases, perturbing the classical computation and comparing to a fixed Louis computation, but more interesting was the other way around, perturbing the Louis computation versus a fixed classical computation. That highlighted a few other things, which is because on the Louis side everything is sorted integers, minimal perturbation there that we can do is 1 bit. It's the next number or the previous number that was there. Where in here we can pretend that we have real numbers and perturb probably small things. That's again not the case, but we can pretend more than we could in Louis. So that also gives you some minimal perturbations that are available to that system. Just on the neuroscience research side, for us it was useful to put that uncertainty of Luhi in context. It's probably useful if Luhi is to be used in any kind of signal processing stage as well. So the main result here was we can't take every model that we can think of here in LIF and port it to Luhi because of constraints in the representation on Luhi. On the other hand, on the neural data side, usually those parameters that come from data where the uncertainty of the parameters themselves is relatively large, which again suggests that there is a whole class of models of the same kind that are compatible with the neural data. In which case, the Luhi uncertainty is somewhere here, something small in the middle of a big cloud of possible models. So it's not necessarily that bad. The statement that from this class of models, classical architecture can simulate a lot of them. Luhi can simulate fewer of them, but still tile the whole set of potential models if you need to simulate. You won't have all of them, you have fewer, still covering what is necessary. One thing that we haven't done yet, we're working on it, it's useful. For all those models, they'll produce some dynamics. And they're data equivalent, so they're compatible with the data, even though they'll produce slightly different dynamics. Now, given the dynamics of data-compatible classical numeric models, where does the dynamics of Luhi lie in this cloud of valid dynamics, which are compatible with the biology that is constrained so far? Yeah, that's interesting for us, but it's also interesting for any kind of signal processing that needs to be done. You have classical signal processing with which everybody's happy and they're used to, and we have this new thing that's, we don't quite know yet what are the constraints. That gives some directions as to how to compare the constraints, doing the sensitivity, and doing this comparison context. Current focus of my lab switched to continued with networks. I spent last year on a sabbatical with colleagues in Germany, Forschungszentrum Munich. They're the developers of Nest. They have several standard networks where because they keep building the system and improving the system, that some of their test cases to make sure that on test cases the system is still the same, continuous integration style. So I wanted to take something like that, port it to Luhi, and do the comparison on network level rather than on single unit level. Okay. The main model is Pottian's Disman 14. That's a cortical microcircuit model. Several layers of the brain, exciter inhibitory populations connected to one another. That turned out to be pretty complicated to configure to Luhi. So we settled on a single one of those, a single exciter inhibitory network. To highlight what this thing is, again, you have a group of neurons that we'll call excitatory, another group of neurons that we'll call inhibitory. Each one of those little dots is a leaky integrating fire or other spiking neuron. They're excited inhibitory because all those connect to the other group or within the group by positive connections on the graph, and all those connect to themselves or to the excited population with negative weights on the graph. Typically, the test networks that we have are the excitatory numbers about 4 times the inhibitory numbers. Yes, that was the case. Observations from data. There's no particular reason for this to be the case. So, current progress here, I'll show some of that. We hit some limitations of Intel compilers, so we could compile networks about 12,000 neurons, 10 million synapses, which from the high performance computing group and Nest, that was laughable. They go with several million neurons and 500 million synapses, for example. But we have to start from some place. And that was, that was mainly issue with the compiler for Luigi 2. Luigi 1, we ended up with about 250,000 neurons, and then they switched the architecture. Something happened in between. That still gives us some results. Part of the things is, okay, that they're saying maybe when they have a bigger box of Luigi, we can run bigger networks. Colleagues in Sandia National Labs in the United States just received this box from Intel with about 1,000 Luigi chips, and in theory it can take about 1 billion neurons. So we'll try that thing there to see what constraints they have. For us, things started well on small networks. This is speed up compared to biological real time. This is Luigi and this is Nest CPU. So we start about 100 times speed up. The HPC chips could run the same networks at about 10 times speed up. However, for still unclear reasons to us, this time the performance degraded a lot more rapidly than we had before. And so at this level of complexity, where instead of the number of neurons, we look at the number of synapses, that's also the main computational bottlenecks. We had one class of networks that started fast and scaled down to about 2 times real time, roughly the same as the classical architecture. And some other class of network, they just had more neurons, not necessarily more synapses, that we don't understand why yet are performing at a lot lower level. We flag them and we'll try to look into finding some reasons. But hopefully this is still compiler issue, so when they fix the compiler, that's going to disappear. What's more interesting for everybody, okay, 2x, yeah, so performance-wise, they were settling to about the same level. What's probably more interesting to everybody was the power consumption of those chips. So again, you have more complicated networks, they draw more power because they use more of the electronics on the chip in both cases, in the Luigi and on the Nest. Where I want to highlight is, note that here we're measuring the power in joules, and here we're measuring the power in kilojoules. So right off the bat, because of the specialized electronics, because of the additional details, additional care that Luigi designers have taken into limiting the use of electricity when parts of chips are not in use, we get about 800 times for those networks, 800 times improvement in power consumption for the same level of performance. So let me see, I think I'll skip that, and those are questions coming from there. So part of the questions are thinking about analog electronics as well, where again they're going to be doing something that we control only to some degree, and we started asking, okay, well, can we resolve this problem mathematically? Like, we want this computation to happen. We know that this computation is happening. Is there some function that would map one into the other? And started looking at ideas of topologically equivalent dynamical systems, in which case deep nets seem to be a good tool to provide maps like that, either change of coordinates or equivalences between, say, this trajectory and that trajectory that would allow us to use a really fast but more constrained system to compute something more flexible of interest. I spent a lot of time on that. When you're a mathematician, having something that says the diagram commutes is actually very pleasant. So I wrote it here. The other thing, and this, we've been looking at that, but with lower priority. Now it's elevating in priority a little bit higher after talking with Mr. Ivanov. The spiking neural network structure. And in some sense, it's scary. You have those events, they're not differentiable. A lot of the tools that we develop for deep nets and for recurrent nets don't seem to work. Lucky for us, there were some very good mathematician engineers, Lazar and Todd, that started working in that about 20 years ago. It took a while for even the neurocomputation community to take into account, and it's still not very widely accepted. But they looked at the same problem. So we have a continuous signal. How can you represent it with discrete events? Turns out there's even older engineering result. This is roughly sigma delta modulation. What they did is convert that to neural representation, and you can see and track it here. This is your input. This is roughly your neuron bias. The neuron have other parameters and dynamics. It's integrated, compared to threshold. The delta part is refractory period in level, and allows you to take a continuous signal and represent it with events. Everybody can do that. The important part is and what part of the information is preserved. In classical signal processing, where you have uniform time sampling, there is a Shannon-Nyquist limit that tells you how often you need to sample. Here, this is the idea of non-uniform time sampling. You sample when the signal changes. If the signal changes slowly, you sample less often. If the signal changes more rapidly, you sample more often. So this is the sampling of a continuous signal, and you see the non-uniform part. And here is a reconstruction. You feed the spikes back to a reconstructor, the same way you do with Shannon, and you get a reconstructed form of the signal. It's very difficult to see the two, and this is a graph that engineers would love very much, where you can get the reconstruction down to the minus 80, minus 100 decibel, which means very, very high quality reconstruction. And there is which I haven't put here, there is a controllable loss of quality, which is again a trade-off. You can sample with fewer spikes, but then the quality of your reconstruction is going to be worse. So, nice trade-off. Fewer spikes typically mean less energy spent. So if you're willing to trade off quality of signal against energy, we have a tool with which to do that. So one last slide on training. This is still under development. Both recurrent networks and spiking neural networks are more difficult to train compared to deep neural networks. There's less of an industry around that. There are several backprop-like algorithms, like reinforcement learning. There's backprop through time, eProp, surrogate gradient, event prop. and several local rules which are supported on hardware, but they tend to be less powerful, so the results achieved with them are lower quality compared to the backprop type algorithms. And there is active research in trying to find even better algorithms here to make it more competitive to deep neural networks. As a summary, our experience has been neuromorphic systems are capable, efficient computers. Their capabilities in theory should be able to outstrip DNN. In practice, that's the beginning of that still. A lot of work to be done to assess, validate them around specific models, similar to the work that's happening in deep neural networks with low precision quantization. It's interesting for us, new mathematical questions are emerging. What's equivalent dynamics? What's equivalence at different spatial and size scales and temporal scales? And what other tools from modern mathematics may be able to help? A lot of the work is from Dr. Srijani Day and current PhD candidate Jacob Pennington. And I want to thank my collaborators, Allen Institute, Intel Labs, University of Arizona, Forschungszentrum Jülich, and University of Tennessee, and close with that and open for questions if you have questions. Thank you. And I don't know how questions from YouTube will be handled. If anybody asks anything,
it would be interesting also to see the questions from YouTube from the presentation. But let's start with the audience here.
Oh, I have a question.
Please.
You didn't said anything about simulating different kinds of neurons. It is possible to have different kinds of neurons?
I briefly mentioned it, maybe too briefly. So Intel had one set of built-in simulations where the simulation was in electronics. With the new chip, they have microcode on which they've written 2 or 3 slightly different neurons, and several research groups have expanded with a few more neurons. So, for example, one of the exciting new neurons available there, I think well validated, is the Izhikevich neuron, which is a 3-state neuron with a lot of nonlinear dynamics. So the microcode is not a complete code set. It can multiply now, so produce some dynamics. I think the Izhikevich has up to a cubic there. And that already created a lot of problems to the group developing it. So, but that's what I mentioned. There is an option. People are working on expanding. So internally, Intel produced several other units that are not really neurons, but they're using them very heavily in their optimization code to do some dynamics. So that's part of the slowly building part, get more variety of neurons.
And what about, for example, in the brain, we don't have a massive connection, but we have different topologies that the neuroscientists are trying to figure out how they are connected and how I understand that we currently don't have so many neurons in the prototype, but do you believe that in the future, you'll be able to reproduce these topologies in order to create small organs, let's say, just like we have the different structures in the brain?
So briefly, yes. We're still working on it. There are some more elaborate networks that are being used, but it's growing slowly. There are not that many people, so there may be these days about 200 research groups that are engaged with Luigi at different levels. There are others that work in different neuromorphics, of course. I anticipate that more innovation would come from the robotics community because they actually have very specific tasks and they want them done. And they want them done now.
Yeah, that's a question that I had, the same vein that Goodney has asked. When you compare a system like that to a particular brain function, do you think it would be more efficient, or
Not yet.
for a very simple task like the
Yeah, not yet. So Luigi is still digital electronics. So it's very fast. It depends how you measure efficient. It's electronics, so we can get it up to 1,000 times faster than biological real time. But it's electronics, it's digital electronics, which means they're still pumping currents here and then dumping them to heat. That even though it's a lot more efficient, there is the limitations of digital electronics. Analog electronics, on the other hand, yes, it can get more efficient once we figure out how to deal with it.
I'm a professor of robotics, so I'm very interested in that. But you mentioned the encoding process. This is an issue even when we use spark neural networks in computers because we have to do all the process from the temporal data. Do you do it on board, on the chip, or this is a process?
You mean the encoding?
Yeah.
Can be done either way. Efficiency is different.
Mm-hmm.
So these days there are several exciting new sensors coming into play that produce events.
Mm-hmm. Yeah.
There is the DVS, the event camera,
Yeah.
that several companies are producing that.
Mm-hmm.
I think there is a event-based microphones that again produce spikes.
Okay, so the idea is that the sensors come
The
in this
sensors
way. Okay, you
come
don't
to
do
be-
this. Yeah.
Yeah,
because
you try not to do it.
Yeah.
If you don't have the sensor, of
Yeah,
course,
yeah, you have to do it.
that.
You have to do it as we do in software. Okay.
For some peculiar reason, there is an event-based olfactory sensor. People are just having fun. I don't know. Do you use a lot of olfaction in your robots?
Not yet.
But that could be a good industrial sensor for chemical enterprises.
Well, in terms of applications, I was wondering what the different kinds of applications that you can build with these neural nets instead of simulated neurons that could be useful.
They are simulated, so in principle they can do the same thing. They're just research-wise they're a little bit behind because they're harder to deal with, and two, over the last 15 years, deep nets have just exploded, and a lot of people are dealing with them. So with a lot of manpower, you can do more things. As applications, Intel was showing they worked with Deutsche Bahn, for example, and they were doing optimization of their train schedule. Having spent a year in Germany, I'm not super impressed with their optimization of their train schedule, but they can do it better than standard computers, let's say that. Interesting that other companies, SpinCloud, that's working on Spinnaker, they have a industrial project with some German farm where on the edges, on the sensor, they were using Luigi processors to do initial signal processing. So somehow they decided that their Luigi is better than their processor to do that kind of optimization, that kind of processing. And here and there, there are several groups, I don't follow them very closely, but there are several groups that work on drones, quadcopters, and so on, that are experimenting with Luigi as either vision processor or as control processor, like flight dynamics, etc. And any idea that you have, Intel's going to be happy to hear it.
Well, in fact, I have an idea because There are some people working with consciousness that are proposing that together with the processing of neurons, there is some kind of parallel processing using glial cells. And in this case, we have two parallel networks, a network with neurons and a network with glial cells. And in some sense, they have some interaction, and the glial cells are used for making broadcasts. I was wondering if such a kind of simulation will be possible in the future.
Surprisingly, yes, and it was done. There's a group in Rutgers, Konstantinos Michmizos, who's doing robotics and started working on Luigi. So he created a simulation of glial cell connected to neuronal networks because he needed it for his walking robots, I think.
Interesting.
It is there. It's open source. You can go and give me some contact, and I'll send you the link to that. That was quite interesting 2-3 years ago. I haven't heard much after that, but I'm also interested in that. Yes, there's a lot of glial networks that they're becoming more and more important in the understanding of biological neural systems. And corresponding when we do neuromorphic, we start asking, so all those synapses, now in biology, most people talk about tripartite synapse, which is the input, output, and the glial cell that's wrapped around it. That's a lot of modulation. We can't wrap electronics, but we can simulate some. Anybody from YouTube?
No question.
Okay, we'll take it separately.
Absolutely.
Okay, thank you.